The important thing is to never stop questioning. That's a quote that really resonates, doesn't it?
It really does. Perfectly sets the tone.
Absolutely. It captures the spirit of science, and it's perfect for our deep dive today. Welcome, everyone, to The Deep Dive. We're plunging into the most fascinating scientific breakthroughs, exploring how they change our understanding of the world. And today we're tackling a phenomenon that's absolutely fundamental to modern electronics, to our grasp of materials, the Anomalous Hall Effect, or AHE.
Right. Something scientists felt they had a good handle on for, over a century?
Exactly. But, as often happens in science, what we thought we knew is being, brilliantly reevaluated. So our mission here is to unpack a really groundbreaking new interpretation of AHE. It was just published in APS, a top physics journal. And this new work, it offers a comprehensive and, frankly, pretty revolutionary description of the magnetic behavior behind this effect. It's turning some old ideas upside down.
And, this isn't just abstract physics. This deep dive is especially relevant for you listening. Maybe you're a UPSC aspirant tracking current science developments for your exams. This is definitely key.
Oh, absolutely.
Understanding complex science, its implications, that's crucial for mains. And the specifics, the definitions. Definitely useful for prelims, too.
And even if you're not preparing for exams.
No, it's just fascinating for anyone curious about how science actually works, how our understanding evolves. It's about seeing the frontiers of knowledge being pushed.
Okay, so let's get into this century-old mystery. Where did the story of the Anomalous Hall Effect, the AHE, actually begin?
Right, well, you have to go back to 1879. Edwin Hall. He discovered the ordinary Hall effect first.
The ordinary one, okay.
Yeah, picture this. Current flowing through a flat conductor. You put a magnetic field across it, perpendicular, and a voltage appears sideways, perpendicular to both the current and the field. Like the charges are being pushed aside by the field. Makes intuitive sense.
Seems straightforward enough. But then, just 2 years later, something anomalous happened.
Exactly. Hall found the very same kind of transverse voltage, but this time in ferromagnets, things like iron.
Oh.
But here's the kicker. He found it without any external magnetic field applied.
Wow. Okay. So the effect was just there on its own.
Precisely. It seemed to be coming from the material's own internal magnetization. That was the anomaly. It shouldn't have happened, according to the thinking back then.
So they called it the Anomalous Hall Effect. Aptly named.
Very aptly named. And the mystery started right there.
And this wasn't just some scientific curiosity tucked away in a lab, right? It had real impact.
Oh, massive impact. Even while parts of it remain puzzling, the AHE, along with the ordinary Hall effect, really helped kickstart semiconductor physics, solid-state electronics.
So the basis for a lot of modern tech.
Pretty much. Think smartphones, computers, the principles AHE helped uncover are foundational, and more recently, it's been absolutely central to this exciting merger of topology and condensed matter physics.
Topology and physics, that's a whole fascinating area itself.
It is, and AHE is right there helping us understand these new quantum materials and their potential.
So for decades, how did physicists try to explain this AHE? What was the standard story?
Well, for a long, long time, the main idea, the conventional view, was that AHE was caused by magnetization breaking something called time reversal symmetry.
Time reversal symmetry. Okay, what does that mean simply?
Imagine running a film backward. Most physical laws look the same, but magnetism, related to electron spin, breaks that. If you reverse time, the magnetic field, the spins, they flip.
Got it.
So the thinking was, because ferromagnets have this internal magnetization, they inherently break time reversal symmetry, and that's what causes the AHE.
So the Hall effect was directly tied to the strength and direction of the magnetization.
Exactly. The Hall resistivity was usually described as being linearly dependent on magnetization. And the current was deflected perpendicular, always perpendicular to that magnetization direction. It seemed neat.
A neat picture. But science rarely stays neat forever, does it? Recent experiments started finding problems.
That's right. Cracks started appearing in that neat picture. Researchers began observing things that just didn't fit.
Like what, specifically?
Well, for one, they found AHE could actually happen even when the Hall deflection plane was parallel to the magnetization.
Parallel, not perpendicular.
Exactly, a direct contradiction to the standard model. And then, the Hall resistivity itself. It often showed complex, nonlinear behavior, not that simple straight-line dependence on magnetization.
Okay, so parallel deflection, nonlinear behavior. What else? You mentioned antiferromagnets earlier.
Ah, yes, that was perhaps the biggest puzzle. Antiferromagnets. These are materials where the magnetic moments inside point in opposite directions, canceling each other out.
So no net magnetization overall.
Correct. Zero net magnetization. And yet, experiments found some antiferromagnets showed a significant AHE.
How could that be if the effect supposedly relied on net magnetization?
Precisely the question. The conventional theory just had no answer for that. It was a clear sign something fundamental was missing from the picture.
So with these puzzles piling up, what was stopping theorists from figuring it out? What was the core challenge?
Well, a big part of it, from a theoretical standpoint, was an energy scale issue. The energy linked to magnetization itself is typically quite large. We're talking electron volts.
Right.
Trying to incorporate the subtler effects, these higher order things needed to explain the anomalies, using the existing mathematical tools specifically, perturbation theory was incredibly difficult.
Because the main effect, the magnetization, was just too dominant.
Kind of like trying to spot tiny ripples on a massive ocean wave. The sheer scale of the magnetization energy made it hard to properly account for the smaller, more complex interactions within those frameworks. It really put limits on the old time reversal breaking idea.
Okay, so the stage was set for a new idea. Enters Zheng Liu and his colleagues.
Exactly, from the University of Science and Technology of China. Their work, published in APS, proposes this fundamentally new way of looking at AHE.
And it's a radical shift, you said. They're saying it's not just about time reversal symmetry breaking by magnetization.
Right. They reinterpret AHE as being fundamentally driven by symmetry breaking caused by something else entirely. Spin-orbit coupling, or SOC.
Spin-orbit coupling. Okay, let's break that down. What is SOC?
Simply put, it's an interaction inside an atom. An electron has an intrinsic spin, like it's spinning on its axis, and it also orbits the nucleus. Spin-orbit coupling is just the interaction between that spin and its orbital motion. They influence each other.
Okay, so an internal interaction within the electron's behavior. Why is focusing on this interaction the key to the new theory?
Well, there are a couple of reasons. Crucially, SOC is typically a much weaker interaction than the magnetic exchange that aligns spins.
Weaker? How does that help?
It means it's much more suitable for those perturbation techniques we mentioned. The mathematical tools work better when dealing with smaller energy scales. It makes the problem more tractable.
I see.
And it's worth noting this wasn't entirely out of the blue. Earlier studies had already started bringing in concepts like the Berry phase.
Berry phase? That's
Yeah.
related to the geometry of quantum states, right?
Exactly, a quantum geometric effect. And those studies had already hinted that in collinear magnets like simple ferromagnets where spins mostly align, the AHE wasn't just for magnetic moments, but also involved SOC effects. Liu's work builds on and crystallizes this.
Okay, so SOC is the fundamental driver. Now, you mentioned symmetry breaking. What symmetry is SOC breaking here? This leads us to the spin group concept, which sounds important.
It is critically important. We're used to talking about magnetic group theory to describe symmetries in magnetic materials.
Right.
But this new work argues we need something more comprehensive, a spin group. It comes from recognizing that electron spins aren't just up or down. They're vectors, they can rotate.
So there's a symmetry related to the rotation of spins, separate from the crystal lattice symmetry.
Precisely. Especially when SOC is weak or ignored. Symmetries in spin space can exist independently.
Can you give an example?
Sure. Think about a material becoming ferromagnetic when cooled. That transition corresponds to the breaking of spin-rotation symmetry. The spins pick a direction.
Okay.
Now, the idea of spin groups isn't brand new. It emerged decades ago. But the full mathematical framework for it has only been properly developed quite recently, and that's what Liu and colleagues are leveraging.
So how does SOC fit back in to break this spin group symmetry and cause the AHE? It sounds subtle.
It is subtle, but that's the key insight. In magnetic systems without SOC, there's a combined symmetry operation. You perform time reversal, then you rotate all spins by 180 degrees.
Okay, like an effective time reversal just for the spins.
Exactly. And this combined symmetry, if it holds, actually forbids things like AHE.
So SOC breaks that specific combined spin space symmetry.
Yes. By introducing spin-orbit coupling, you break that effective time reversal symmetry within the spin group. And the theory shows that the anisotropy of the AHE, why it can be parallel or perpendicular depending on the material, arises precisely from how SOC breaks this spin group symmetry.
That's fascinating. It's a much deeper level of symmetry breaking.
It really is.
And based on this, Liu and his team developed a new formula, right? A multipolar expansion law.
That's correct. Using the structure of spin groups, specifically in collinear ferromagnets, they derived a more complete mathematical description for AHE. It replaces that old, simple linear formula.
What does this new law capture that the old one missed?
Think of it as going from a basic model to a high-fidelity one. It includes multipolar terms that can describe those complex, nonlinear behaviors and different orientations of the AHE that were previously unexplained.
So the theory sounds powerful, but does it match reality? What's the experimental proof?
The validation has been really strong, actually. The first term in their expansion, the dipolar term, successfully explains that in-plane AHE.
The one where the voltage is parallel to the magnetization.
Yes, the one observed in low-symmetry materials that the old theory couldn't handle. This new law accounts for it naturally.
And you mentioned higher-order terms predict this in-plane effect could be common.
Exactly. The nonlinear characteristics predicted by the higher-order terms suggest the in-plane AHE isn't just some exotic exception, but could be quite widespread in different magnets.
And has that been seen?
It has. Very recently, this in-plane AHE has been directly observed in common everyday ferromagnets like iron and nickel.
Wow. Iron and nickel. That's strong evidence.
Incredibly strong validation for the theory. It really underscores how fundamental symmetry and symmetry breaking are in physics.
So the spin group framework gives us a new tool.
A powerful new lens, yes. It helps us study various SOC effects and, crucially, disentangle what comes from magnetic interactions versus what comes from spin-orbit coupling.
And it might apply beyond AHE.
Definitely. The team suggests this framework could be applied to other related transport phenomena, like the nonlinear Hall effect, the spin Hall effect, offering a more unified understanding.
Does this extend to other types of magnetic materials too, not just ferromagnets?
Absolutely. That's another exciting aspect. The understanding can be directly extended to other magnetic orders. For instance, altermagnets.
Altermagnets. They're relatively new on the scene, aren't they? No net magnetization, like antiferromagnets, but different properties.
That's right. They have a specific collinear magnetic order combined with crystal fields that leads to spin splitting, even without net magnetization. And guess what? Their behavior is also described within the spin group framework.
Interesting. And non-collinear magnets.
Yes, materials where spins point in complex, non-aligned directions. The theory applies there too. It really opens up exploration across a wide range of magnetic systems.
So it sounds like this has really cleared up a long-standing puzzle and opened new doors.
I think that's fair to say. A broad pathway is now open for exploring all sorts of emergent quantum phenomena in magnetic materials using spin group symmetry as the guide. It's a real step forward for the field.
Okay, let's recap the aha moment here.
Yeah.
We've gone from thinking AHE is mainly about magnetization breaking time reversal symmetry
to understanding it's more fundamentally about spin-orbit coupling breaking a deeper symmetry, a spin group symmetry.
And this new view, published in APS, finally gives a comprehensive explanation for AHE, solving those old puzzles like the effect in antiferromagnets and the in-plane voltage.
Exactly. And for you listening, this really shows science in action, doesn't it? How paradigms shift, how new tools like spin group theory lead to deeper insights.
It highlights that dynamic nature of science.
Precisely. And how fundamental physics keeps revealing secrets behind phenomena that directly impact technology and how we see the universe. That's crucial knowledge, whether for exams or just for understanding our world.
It leaves you wondering, doesn't it? If a phenomenon we thought we understood reasonably well for over 100 years, like the Anomalous Hall Effect, still held these hidden layers, what other areas of science, maybe ones we consider settled, are just waiting for a new perspective, a new theoretical lens to reveal even deeper truths?
It's a great thought to ponder. Never stop questioning, right?
Indeed. Well, thank you for joining us on this fascinating deep dive today. If you found this discussion useful or intriguing, please do like this deep dive and subscribe to our channel for more explorations like this. And please comment below any questions or topics you'd like us to tackle next. We really do value your input. Thanks for listening.